For the first time in millions of years, Earth's natural cycles are breaking formation. The planet's long, predictable heartbeat follows a slow rhythm of ice, then warmth, repeating for ages. But that rhythm is suddenly changing. Something in the pattern has shifted, and the record shows it clearly. Tonight, on The Galaxy Scientist, we drift through those ancient cycles and gently trace where the pattern begins to break, and what that quiet shift might mean for the world you'll wake to tomorrow. If this kind of soft wondering feels right to you, a gentle like and subscribe. Help others find their way here. For now, settle in as we begin together, unhurried and warm. If you feel you understand the weather of our world, the Earth is probably still a step ahead of you. We all know the climate can be fickle. The air seems to change its mind again and again. Temperature rises and falls. Rain arrives and slips away. Winds twist and fade. Tides creep in and out, often with no obvious pattern. Even people who spend their lives forecasting it can only see a short way into the future. It is not because they are careless. It is because the machinery that moves our skies and oceans is woven from countless overlapping threads. High above you, even in the stillness of night, the planet is wrapped in layers of motion. There are quick cycles and slow ones, gentle shifts and powerful swings. Some come from the way the Earth spins and leans. Some are pulled into being by the moon and the sunday. Some begin deep underground, where molten rock and liquid metal flow in heavy, slow currents. On any given day, the weather you feel on your skin is the sum of all these hidden rhythms meeting in one place and time. This is why the arguments about our influence on climate can feel so tangled. Some voices say that humanity is far too small to disturb something as vast as the sky. Others speak as if every storm and every heat wave carries our name. Between those extremes lies a softer question. Among all these natural cycles, where does our own reflection appear? How much of what we feel now belongs to the Earth's ancient habits, and how much comes from what we have done with fossil fuels, forests, and cities? To even begin to answer, we need a sense of how the Earth behaves when no human industry is involved at all. Over deep time, our world has slipped in and out of ice ages, warmed and cooled again and again. Those changes were guided by slow, patient patterns written into the way the Earth moves through space. There are also smaller, familiar patterns that give us the comfort of seasons. All of them leave a signature on the climate we live inside. If you let your thoughts drift outward, you can almost see it. The room around you fades, and the Earth appears instead, a small blue globe, leaning slightly as it circles the Sunday. That lean, or tilt, is the reason so many of us know spring, summer, autumn, and winter. Because the axis of the Earth is tipped, one hemisphere leans toward the sun for part of the year, drinking in more direct light, while the other leans away and receives a softer, slanting glow. When your part of the world leans toward the sun, sunlight falls more straight on. Its energy is concentrated, like the bright circle a lamp makes when it shines directly on the floor. Days stretch longer, and the air has more time to gather warmth. When your hemisphere leans away, the same light arrives at a shallower angle. It is smeared across a larger patch of ground, and its strength is diluted. We give these moods of the year familiar names. Summer when we lean in, winter when we lean out, and the gentler seasons that sit between, closer to the poles. This tilt shapes life in dramatic ways. In far northern towns, such as Tromsø in Norway, the sun can remain above the horizon for weeks during summer, sliding around the sky without fully setting. In winter, it may never truly rise, leaving the landscape in a long, blue twilight. Near the equator, by contrast, the length of day and the height of the sun change much less. Seasons there are often marked more by rain and dryness than by cold and heat. Yet the same simple question still rules. At what angle is sunlight meeting the ground? Straight on, and the equator hums with warmth. At a slant, and the polar regions stay locked in ice. It would be simple if this tilt and orbit were fixed forever. But the universe rarely chooses the simplest story. Our path around the sun is often drawn as a neat circle on the flat plane of the solar system. But in truth, it is slightly stretched and always under gentle pressure. The sun is the main source of gravity, yet the giant planets are quietly involved as well. Jupiter, with a mass more than 300 times that of the Earth, and Saturn, with a mass close to 100 times our own, tug on our orbit as they move along theirs. Because each planet moves at its own speed, these pulls do not cancel. They create a slow, complicated dance. As a result, the shape of our orbit and the way we are tilted do not stay exactly the same. Over very long spans of time, they shift back and forth in regular patterns. These deep rhythms are called Milankovitch cycles, named after the Serbian scientist Milutin Milankovic, who traced them in the early 20th century. They are like slow pulses in the story of the Earth, beating over tens of thousands and hundreds of thousands of years. One of these cycles alters how stretched our orbit is. Across roughly 100,000 years, the path the Earth follows around the Sun becomes more elliptical and then more circular again. When the orbit is closer to a perfect circle, our distance from the Sun barely changes over the year, and the amount of sunlight reaching us stays relatively even. When the orbit is more elongated, there are parts of the year when we are slightly closer to the Sun, and parts when we are slightly farther away. Closer means a little more energy. Farther means a little less, and that gentle difference nudges the balance of our seasons. Right now, we are in a phase where the orbit is fairly round, but not perfectly so. There is still a small but real gap between our closest and farthest points. The time when we are closest to the Sun, called perihelion, arrives in the first days of January. The time when we are farthest, called aphelion, comes in the first days of July. For those living in the Northern Hemisphere, that means part of their winter includes a period when the whole planet is slightly nearer to the Sun, and part of their summer comes when it is slightly farther away. Even with a nearly circular orbit, this still matters. The Earth receives several percent more solar energy around perihelion than it does around aphelion. In the north, that softens winter and takes a little edge off summer. In the southern hemisphere, the effect leans the other way. Their summers arrive when the Earth is a little closer to the Sun, and their winters when it is a little farther away. That can make their warm season feel more intense and their cool season sharper. Over the full sweep of this Milankovitch cycle, as the orbit becomes more stretched, that contrast in sunlight grows from just a few percent to well over 20%. Over long ages, such a change can tip the planet toward deeper freezes or milder times. Another slow-motion rhythm is always at work, swapping the roles of the hemispheres over very long spans of time. The axis of the Earth wobbles. You can think of a spinning top as it begins to slow, the point of its spin tracing a small circle. Our planet does something similar. This motion, called precession, takes about 26,000 years to complete one loop. Because of it, the direction our axis points changes little by little. At the moment, from the northern hemisphere, the star Polaris sits close to that line, which is why it is our North Star. But this is only a temporary arrangement. In thousands of years, another star will stand in that place, and much later, Polaris will return. Precession also shifts how our tilt lines up with our orbit. In around 13,000 years, the timing of the seasons will be reversed in a subtle but important way. The northern hemisphere's summer will happen near the point where the Earth is closest to the Sun, while its winter will fall near the farthest point. The southern hemisphere will find its summers gentler and its winters softer. All of these motions can give you cold winters and hot summers, but they are still measured in months. The deeper story of climate change over ice ages stretches across many thousands of years. Some Milankovitch cycles help decide when glaciers grow and when they retreat. We do not yet have a perfect explanation for how ice ages begin and end. There are many ideas, and some pieces still do not fit together. Even so, the timing of certain long glacial periods lines up so well with these orbital cycles that it is hard to ignore the connection. One of the quieter shifts involves the plane of our orbit itself, the thin sheet of space along which we travel around the Sunday. Over spans of roughly 100,000 years, that plane tilts very slightly up and down. The distance to the Sun does not change, so at first it is not obvious why this would matter. Yet the record of ice over the last several 100,000 years rises and falls almost in step with these tilts. Some scientists have suggested that the regions of space we pass through may carry thin clouds of cosmic dust. When our orbit lines up one way, more dust might lie between us and the Sun, gently dimming the light. When it tilts another way, the path may clear, and more sunlight reaches the Earth. A tiny, persistent difference in light, stretched across many thousands of years, could be enough to let ice sheets spread or shrink. There is another cycle, though, that may matter even more for the world we recognize today, and it sits at the heart of how we experience seasons. It is the change in the angle of the tilt itself. The Earth does not always lean by the same amount. Over roughly 41,000 years, the tilt slowly swings between a little more and a little less, from just over 22 degrees to almost 25 degrees. At the moment, the tilt is a little above 23 degrees and is gradually decreasing. At first, that might sound comforting. A smaller tilt means less contrast between summer and winter. The path of the Sun across the sky shifts less between seasons, and temperatures may feel more moderate. You might imagine that this would make ice ages less likely, that softer seasons would keep the world open and mild. Yet the climate story has a quieter twist. When the tilt is smaller, summers in high latitudes are not as warm. Snow that piled up in winter on mountain peaks and in polar regions does not fully melt. Year after year, a little more remains. It compacts into ice, bright and reflective, sending more sunlight back into space. As that reflective shield grows, the planet cools further, allowing even more ice to survive each year. Left to its own slow rhythm, the current decrease in tilt would guide the Earth toward another broad spreading of ice sheets, a cooling that would reach its height many thousands of years from now. In this process, it is not the bitter cold of winter that matters most, but the surprising gentleness of summer. You see, when winters arrive, snow naturally gathers on high ground and near the poles. In truly warm summers, most of that snow would quietly melt away. However, when summer is gentle enough, the snow does not quite surrender. It lingers on mountaintops and in high valleys instead of melting away, and each new winter lays another layer on top. Over time, that bright cover becomes a more permanent part of the landscape. Snow and ice are pale and reflective. So much of the sun's light bounces back into space instead of warming the ground. The more of the planet that is wrapped in this shining skin, the less energy it keeps, and the colder it becomes. That extra chill lets still more snow survive the next summer. In more than one sense, it really is a snowball effect. We are living in an interglacial, a relatively mild pause in a much colder rhythm. For most of recent geological time, large ice sheets have claimed huge areas of the northern hemisphere, advancing and retreating over tens of thousands of years. From a technical point of view, we are still inside an ice age, because massive caps of ice still rest on Greenland and Antarctica. It is just that, for now, the ice has drawn back enough for forests, grasslands, and cities to spread. Left entirely to itself, the slow choreography of Milankovitch cycles would eventually guide this interglacial toward its end. Over thousands of years, shifts in our orbit and tilt would once again favor summers that are just cool enough for snow to linger. Year by year, ice sheets would creep outward, and the planet would slide into another long winter. These changes move with the patience of mountains, but given enough time, they can redraw the face of the world. That picture, though, assumes that orbital cycles are the only things that matter. The record written in deep ocean mud and polar ice shows repeating patterns, cold eras returning roughly every 100,000 years, with smaller warm pulses on the order of tens of thousands. The timing fits Milankovitch cycles so well that it is hard to dismiss. But the Earth is not only a stone in space. It is wrapped in air, and the chemistry of that air has its own quiet power. Two of the most important gases in that thin envelope are carbon dioxide and methane. They are greenhouse gases. They let most of the sun's light in, but they make it harder for some of the outgoing heat to escape back into space. Over natural cycles, their levels rise and fall with volcanoes, the growth and decay of plants, changes in the oceans, and many other processes. When there is more of them, the planet tends to warm. When there is less, it tends to cool. Here, feedbacks show up again. Just as ice growth can feed on itself, so can ice loss. When snow and ice shrink, they uncover darker rock, soil, and open water. Darker surfaces absorb more of the sun's energy instead of reflecting it. That extra warmth melts still more ice, exposing still more dark surface. A small shift at the beginning can, over time, grow into a much larger change. If the only forces at work were Milankovitch cycles and natural greenhouse gas swings, our far future would probably be a colder one. The tilt of the Earth's axis is currently decreasing, which, without any other influence, would favor mild summers at high latitudes. In such summers, some of the winter snow would never quite melt away. Over many thousands of years, that leftover snow would thicken into ice sheets, and a new glacial peak would be expected roughly 10,000 years from now. That cold world lies far beyond any single lifetime, but on the scale of Earth's history, it is not very distant. For now, though, our particular place in the Milankovitch cycles tends to keep temperatures fairly moderate. Our orbit is not extremely stretched. Our tilt sits in the middle of its range, and the slow wobble of our axis is not at a particularly extreme point. In that sense, the orbital side of the story is trying to keep things relatively even. These deep cycles are part of the background rhythm, slow and steady, not the sharp twists we feel from year to year. Among the shorter climate cycles, riding on top of that background is one that almost certainly has brushed against your own life, whether you recognized it or not. The El Niño Southern Oscillation, often shortened to El Niño and La Niña. Its heartbeat begins in the tropical Pacific Ocean, but its influence ripples outward across nearly every continent. Changes in rainfall, drought, storm tracks, and even food availability have all been linked to its shifting phases. In recent decades, some of its stronger events have coincided with intense floods, prolonged dry spells, famines, and mass die-offs of marine life. People along the coasts of South America had noticed this pattern long before scientists gave it a formal name. Centuries ago, fishermen there spoke of a recurring time of unusually warm water and poor catches that often peaked around Christmas. They called it El Niño de la Navidad, the Christmas child. Much later, researchers began to see that strange weather in very distant places could be connected to the same underlying cycle. By the middle of the 20th century, it was clear that El Niño and its cooler counterpart, La Niña, were both phases of a global pattern that tends to swing every few years, usually between about 2 and 7. To understand why, it helps to picture what normal looks like across the Pacific before El Niño or La Niña arrive. Under typical conditions, near the surface, winds blow along the equator from east to west. These are the trade winds, shaped by the way the Earth spins. They push warm surface water away from the coasts of South America toward Asia and Australia. Warm water piles up in the Western Pacific, while colder, deeper water rises to the surface along the shores of the Americas to replace what has been pushed away. This upwelling brings nutrient-rich water from the depths into the light, feeding vast blooms of tiny phytoplankton. Those, in turn, support fish, seabirds, and marine mammals. Coastal communities depend on this hidden conveyor belt of cold, fertile water. Because the system is delicately balanced, any change in the trade winds sends ripples through it. El Niño is the name given to one of those changes. During an El Niño phase, the trade winds weaken. They do not push as strongly on the ocean's surface. So, the warm water that would usually be driven westward relaxes back toward the central and eastern Pacific. Upwelling along the South American coast slows. Less cold water reaches the surface, and the sea there grows warmer and poorer in nutrients. Fish that rely on the chill, rich water either move away or die, and the people who fish for them feel the loss. The atmosphere notices too. The newly warmed Central and Eastern Pacific heats the air above, causing it to rise, and shifting where clouds gather and where rain falls. High above the Pacific jet stream, a swift river of air that usually follows a certain path across North America, tends to sag southward. As a result, the northern parts of the United States and Canada often become milder and drier than usual, while the southern United States and the west coasts of Central and South America can grow wetter. Countries such as Peru and Ecuador, which normally expect a certain rhythm of rainy months, may find themselves facing far more rain than they can safely handle during a strong El Niño. Rivers swell, hillsides give way, and low-lying neighborhoods can be buried in mud. Many thousands of people have lost homes and livelihoods during such years, simply because warm water shifted eastward across the ocean. On the opposite side of the Pacific, the pattern reverses. As the main column of warm rising air and heavy rain moves toward the Central and Eastern Ocean, places like South Asia and Australia can be left under clearer, drier skies. In India, monsoon rains may weaken or arrive late, hurting crops. In Australia, long dry spells leave grasslands and forests parched, ready to burn. On a global scale, the average surface temperature of the planet tends to rise slightly during El Niño events, by about 1/10 degree Celsius. It sounds small, but when layered on top of the background trend of human-driven warming, It can help push individual years to new records. Not every El Niño is strong, though. Some are mild, their effects subtle outside the regions most directly touched. Most last roughly 9 to 12 months, although a few have lingered for several years. The El Niño Southern Oscillation is not a neat, repeating clock. It is more like a seesaw. After an El Niño phase fades, the system often drifts back through something close to neutral and then tips toward its cooler opposite, La Niña. If El Niño is a disruption of normal conditions, La Niña is something like normal turned up a little louder. During La Niña, the trade winds strengthen. They push even more warm surface water westward, and in response, upwelling of cold water near the Americas becomes stronger. For fisheries along coasts such as Peru and Chile, this can bring a burst of life. The flood of cold, nutrient-rich water feeds large populations of anchovies, sardines, and other fish. Predators like salmon can venture into waters that are usually too warm for them, and even squid may follow the food into new areas. Far across the ocean, the extra warm water pooled near Southeast Asia and northern Australia fuels heavier rains and can increase the number and intensity of tropical cyclones in that part of the world. Over North America, the jet stream is often pushed farther north than usual. This tends to leave the southwestern United States drier, deepening drought, while the Pacific Northwest becomes wetter, with more storms and mountain snows. In recent years, a stubborn La Niña has been linked with an extended megadrought in the American Southwest, so severe that records in long-lived trees suggest it is one of the worst dry periods in more than 1,000 years. La Niña also reshapes hurricane seasons. Over the Atlantic, the changes in upper-level winds often make it easier for hurricanes to form and strengthen, so La Niña years can bring more and stronger storms there. Over parts of the Pacific Basin, by contrast, the same pattern can mean fewer tropical cyclones. The same push and pull in the Pacific can therefore bring very different stories to different coasts. For communities along the western shores of South America, La Niña brings its own challenges. Strong upwelling cools the coastal waters and the air above them, and the climate there often turns colder and drier. Inland, northern Brazil can become wetter at certain times of year, and the lowlands of Bolivia may face dangerous floods as rivers swell. Across the Atlantic in Africa, the seesaw continues. During La Niña years, eastern regions that were wetter during El Niño tend to swing toward drier conditions, while the south tends to be wetter than average. Right now, the great seesaw of the El Niño Southern Oscillation is tilted toward warmth. In the closing months of the year 2023, scientists at the National Oceanic and Atmospheric Administration looked carefully at the Pacific and announced that El Niño had returned. They watched the surface waters in the east-central tropical Pacific and measured how much warmer they were than the long-term average. A number folded into a measure called the Oceanic Nino Index. The most recent reading was about 1.7 degrees Celsius above that average, strong enough to place this event among the more powerful ones in the record. That extra warmth in one stretch of ocean is not just a curiosity on a chart. It reaches into the lives of millions. In India, officials were already warning farmers and cities to prepare for the possibility of weaker rains and dry fields. Elsewhere, people watching rivers, forests, and coasts adjust their expectations too. This is one of the quiet gifts of paying attention to cycles. The more we learn to read these slow signals, the better we can prepare, protect harvests, move people out of harm's way, and soften the blows that might otherwise arrive without warning. There is also a gentler, more distant gift. By studying a cycle like El Niño, we learn not only about one ocean, but about how many parts of the Earth are woven together. A change in wind in the Pacific stirs clouds over South America, nudges drought into Australia, alters storm tracks over Africa, and warms or cools the global average temperature by a small but real amount. Every time we trace one more strand in that web, we gain a little more insight into what it means to shape and sustain a climate. Someday, if humans choose to build long-term homes beyond this world, that insight will not be optional. Terraforming another planet or coaxing an artificial atmosphere into clinging to a small moon or an exoplanet would demand the same kind of understanding. How air, water, rock, sunlight, and life talk to one another. The lesson of El Niño is simple and profound. Small pushes, applied in the right places for long enough, can move enormous systems. For now, we can stay close to home and follow another of Earth's grand patterns. If the phrase, "winter is coming," made you smile earlier, it fits here in more ways than one. High above the ground, an invisible barricade circles the planet, holding back some of the fiercest cold our world can gather. On one side, much of the inhabited world enjoys relatively gentle weather. On the other side, over the poles, lie deep reserves of frigid air, waiting. You can imagine it as a kind of wall around the far north and far south, a twisting ring of wind that keeps the worst of the polar cold corralled near its home. Most of the time, that wall holds. Cold air swirls and circles above the ice, while lower latitudes remain comparatively mild. But every so often, the wall weakens, buckles, or cracks. When it does, the cold surges outward, rushing toward warmer regions in fierce tongues of Arctic air. The name for that pool of spinning cold is the polar vortex. In truth, there are two of them, one crowning each pole, and each is layered. The lower part lives in the troposphere, the blanket of air from the ground up to roughly 10 or 15 kilometers, where most of our weather unfolds and where most of the atmosphere's mass resides. Above that, in the calmer stratosphere, there is a second, related vortex with its own behavior and seasonal rhythm. Both of these great whirlpools of air turn with the spinning Earth, and winds within them can reach speeds of a few hundred kilometers per hour. They exist because the planet is unevenly warmed. Near the equator, sunlight arrives more directly and pours energy into the surface. Air there heats, expands, and rises, leaving behind a region of lower pressure, closer to the poles, where sunlight arrives at a shallower angle, and for fewer hours, air is colder and denser. It sinks and spreads outward, creating regions of higher pressure. Left on its own, this contrast would send air flowing straight from the high pressure at the poles toward the low pressure at the equator, a ceaseless river of cold wind trying to escape the ice. The reality is more intricate. As warm air from the equator rises and begins to move poleward, it cools, loses energy, and falls back toward the surface well before it reaches the pole. Likewise, cold air flowing equatorward warms and rises again before it arrives at the equator. The result is that in each hemisphere, instead of one simple loop of circulation, there are three main cells of moving air stacked from equator to pole. The Hadley cell in the tropics, the Ferrel cell in the middle latitudes, and the polar cell near the pole. Where these different flows meet, their air masses cannot simply blend. Cold air and warm air push at one another along boundaries called fronts. In the north, air spilling away from the pole runs into warmer air pushing up from lower latitudes. Along those boundaries, the polar vortex is hemmed in, pushed and squeezed from all sides. It is not free to slide down over the mid-latitudes whenever it likes. Something has to help curve and contain it. That something is the Coriolis effect, a quiet consequence of living on a rotating sphere. Even as you lie still, you are moving with the Earth. At the equator, the surface is spinning eastward at roughly 1,600 kilometers per hour. Near the poles, the ground traces a tiny circle in the same amount of time, so its sideways speed is close to zero. Because you and the air above you share the motion of the ground beneath, you do not feel that speed directly. But when air begins to move north or south, it carries its old sideways speed into a region where the ground is moving differently. Imagine a parcel of air starting near the equator and heading toward the north. It begins with the fast eastward motion of that low latitude. As it travels poleward, it finds itself above ground that is not spinning eastward as quickly. From the ground's point of view, the air seems to surge ahead, curving toward the east. Over long distances, this bending turns straight, flows into great arcs. Those arcing winds form narrow bands of especially fast air called jet streams. Around each hemisphere, there are at least 4 main jets draped around the planet like fine, high ribbons. The subtropical jet streams sit between the Hadley and Ferrel cells, while nearer the poles, the polar jet streams ring the boundary between the Ferrel and polar cells. These polar jets live a little below the line that separates the troposphere from the stratosphere. They are only a few kilometers deep, but can extend hundreds of kilometers across, and within their cores, wind speeds can rival those of powerful storms. The polar jet around Antarctica is remarkably steady. Over the Southern Ocean, where there are no large continents to break its path, its strong, nearly unbroken winds circle the globe and tightly wrap the cold air over the ice. That circlet of wind helps keep the frigid Antarctic air mostly penned in over its own domain, maintaining a vast, stable vortex. In the north, things are more complicated. Continents, mountain ranges, and warmer seas all jostle the flow. If air moving from the equator toward the pole is bent toward the east by its extra sideways speed, what about cold air moving from the pole toward the equator? At first glance, it should be left behind by the faster spinning ground beneath and appear to curve toward the west. That westward tendency is real, but cold air near the surface drags against the ground and often slides underneath warmer air. Friction slows it. The stronger, faster jet stream above tends to dominate, guiding the larger pattern. The push of the surface winds and the pull of the high-altitude jets create a tension that matters deeply for what happens next. Wrapped around the top of the world, within the stratosphere above the Arctic, there is a special expression of this balance, called the polar nightjet. It forms and strengthens during the long polar night, when the Arctic spends weeks and months without any direct sunlight. In that darkness, the air over the pole cools even more than usual. Pressure at high altitudes over the pole drops compared to the air farther south, and the contrast in pressure feeds faster winds. The stronger the difference, the faster the polar nightjet spins. In midwinter, it can become a tight, swift river of air that encircles the polar stratosphere and cages the cold air above the Arctic. While it is strong and mostly circular, it acts like a barrier. The deepest cold stays locked near the pole, and mid-latitude regions beneath the gentler bends of the jet enjoy more typical winter weather. In those years, the wall holds, but the atmosphere is full of bumps and edges, and the wall is not anchored to anything solid. As the jet streams circle the globe, they pass over coastlines where sea meets land, over mountain ranges, and above regions where other weather systems are already swirling. Each of these features can send gentle ripples upward, little nudges that disturb the jet's smooth path. Temperature contrasts between ocean and continent can tug the jet poleward or equatorward. Even distant patterns like El Niño can shift the way air moves, feeding energy into these waves. Because the polar night jet exists as a balance point between several competing forces, these nudges can have outsized effects. When the jet is disturbed, it begins to weave and wobble instead of following an almost perfect circle. Large-scale undulations, known as planetary waves, develop and can grow, pushing the jet northward in some long arcs and southward in others. The once tidy ring becomes a meandering loop. If the waves remain modest, the cold air stays mostly corralled, just reaching a little farther south in some regions and retreating in others. But sometimes the disturbances build. The meanders become so pronounced that parts of the jet stretch far from their usual latitudes, and chunks of the polar vortex are pulled away from the pole. In the upper stratosphere, one of the clearest signs that this is happening is an event called a sudden stratospheric warming. During one of these episodes, which most often arrive toward the end of winter, temperatures high above the Arctic can jump by tens of degrees Celsius in a matter of days. It sounds paradoxical, a warming event heralding deeper cold for many people below. Yet that is often what follows. The same waves that pour energy into the stratosphere and heat it up can also weaken, twist, or even temporarily reverse the usual westerly winds of the jet. When the winds that circle the pole slow and falter, the invisible wall they form breaks in places. The tight, central whirl of the polar vortex unravels or splits. No longer neatly contained, lobes of Arctic air spill southward. As they move into lower latitudes, they collide with warmer air masses, and the contrast sharpens storms and drives fierce outbreaks of snow and ice. On weather maps, the jet stream looks as if it has buckled, looping far to the south over one continent and curling back to the north somewhere else. Regions such as Europe and large parts of North America, which usually lie on the milder side of the stratospheric polar vortex, can suddenly find themselves under its direct influence. The air turns bitter, winds knife through streets and fields, and temperatures plunge well below what people are used to. In those moments, it feels as though the hidden wall in the sky has failed, and the pent-up cold of the far north has come pouring down. The forces of winter have arrived. You might not have noticed it from where you are, but high above the clouds, one of those great jet stream reversals unfolded in early March of the year 2024. In the thin, cold air of the stratosphere over the Arctic, the usual westward flow suddenly slowed, then turned and surged the other way. Meteorologists who watched these things quietly ranked it among the top 6 most extreme reversals they have ever recorded, with winds racing so swiftly in the wrong direction that the usual pattern was briefly unrecognizable. This time, though, the invisible wall around the pole held its shape. The polar night jet did not wander into wild loops or send deep fingers of Arctic air plunging far into the mid-latitudes. Instead of spilling its stored cold southward, the disrupted winds reached down and drew gases upward. Ozone from lower latitudes was lifted into the polar stratosphere, creating an unusual spike in protective ozone high above the North Pole. It was a strange, quiet trade, a dramatic upheaval aloft, but one whose main legacy was a thicker shield instead of an ozone hole. Within a couple of weeks, the winds settled, turned again, and the jet found its usual direction once more. It could have been much harsher. Not every disturbance in the jet stream becomes a disaster. Often, with enough warning, the practical response is simply to respect the cold, add extra layers, move carefully, Limit time outdoors while the worst of the Arctic air passes overhead. For many communities, a brief visit from the polar vortex means discomfort and inconvenience more than catastrophe. But sometimes the outcome is more severe, and the stories linger for years. In the United Kingdom, during the winter of 2009 into 2010, people still remember what came to be called the Big Freeze. In parts of Scotland, temperatures sank to around -22 degrees Celsius, the coldest readings in nearly 4 decades. Snow lay deep, roads and rail lines were blocked, events were cancelled, and power lines failed under the strain. For most, it was an extraordinary winter to endure and talk about afterward. For some, it was deadly, and lives were quietly counted among the losses. Across the Atlantic, in the early months of 2019, a lobe of the polar vortex broke away and swept down over central and eastern North America. Air that usually circles close to the pole poured over cities and farmland instead. In some areas, once the bite of the wind was included, it felt as cold as -50 degrees Celsius against exposed skin. Snowstorms rolled through, and in that kind of cold, bare hands or faces could begin to frostbite in as little as 10 minutes. Again, the tally afterward included not only stories of remarkable cold, but also people hospitalized with frostbite and others who did not survive. Given enough time, the balance of heat between equator and poles slowly reasserts itself. The great waves in the jet stream ease, and the polar vortex retreats to its usual home. Yet in the northern hemisphere, some degree of jet stream disruption is not rare. On average, events that qualify as a significant breakdown happen several times each decade. If you live in the north, it is almost certain that you will see more winters touched by these outbursts of polar air. Though hopefully not all of them will be as intense as the most famous examples. In the south, the story is gentler. The polar jet stream encircling Antarctica has so far proved much more stable. Only a very small number of events in the historical record show a breakdown there similar to the ones seen in the north, and the detailed mechanisms behind those southern disturbances are still not fully understood. As the planet as a whole warms, scientists are watching closely to see how these high-altitude winds respond. Some lines of evidence suggest that, over recent decades, the jets have been edging slowly poleward on average. Other studies hint that parts of the jet streams have strengthened since the early 2000s. If that is true, it is something to be quietly grateful for. A strong jet is a firm barrier. When it falters, the polar vortex can spill southward for a time. If it were to weaken so much that it failed entirely, the cold of the high Arctic would not just visit, it could linger. The more you learn about these flows, the more the atmosphere begins to feel like a living tapestry. Invisible currents weave over and under one another, tugging, yielding, and finding temporary balance, only to shift again as new patterns grow. Most of this happens out of sight and out of mind. We look up and see only a clear sky, or clouds, or a passing front. We do not see the high, roaring rivers of air that help keep our climate habitable, or the thin, cold walls that protect temperate lands from a harsher sky. Knowing that such a barrier exists, and that it can fail, has a way of deepening your respect for the quiet protections you never asked for. The polar night jet is not just a poetic name for a distant wind. It is one of many guardians, part of the machinery that keeps the worst of the cold where it belongs. Orbital cycles, ocean patterns, and shifting winds all have their part to play in the long story of climate, sometimes nudging us toward ice, sometimes toward warmth. But not all of Earth's great cycles live in the sky or the sea. Some of the most profound rhythms begin far below your feet, in a realm where rock flows and metal moves like a slow, bright liquid. Down there, deep in the mantle and outer core, another kind of hourglass is always running. Its sand is not grains, but patterns of motion and heat, slowly building toward moments of reversal. When those reversals come, they do not merely change the weather. They reach into the invisible shield of magnetism that wraps our world and keep much of the sun's fury at bay. At some point in the future, the magnetic north and south poles of the Earth will swap places. That sentence sounds like fiction, but it describes something that has already happened many times. If you picture the North Pole as a fixed point on a map, that picture is a little too simple. The magnetic pole is a different thing entirely from the geographic pole, and it wanders. In a full reversal, it does more than wander. The magnetic pattern itself reorganizes so that what was once north becomes south, and what was once south becomes north. The implications for human civilization are not trivial. Compass needles would eventually swing the opposite way. Navigation systems would have to be recalibrated. Animals that use the Earth's magnetic field as part of their sense of direction might have to adjust or adapt. Yet it is not the flip itself that most worries scientists who study these events. The dangerous part is the in-between time, the long period during which the field grows weaker and more tangled before it settles into its new configuration. The Earth's magnetic field is one of the planet's great gifts. It deflects a large portion of the charged particles streaming outward from the sun and from distant cosmic events. Without that shield, much more of that radiation would crash directly into the atmosphere and down to the surface, damaging living cells, breaking DNA, and slowly stripping away the gases we breathe. Mars and Venus, the two planets nearest to us, have little or no global magnetic field today. Mars shows signs that it once had a thicker atmosphere and liquid water at the surface. Without a protective field, those gifts were slowly eroded. Our own field is thought to arise from a process called a dynamo, a natural generator deep inside the planet. In physics, changing magnetic fields can create electrical currents, and moving electrical charges can create magnetic fields. Power plants and simple hand-cranked generators rely on these links. Move a magnet through a coil of wire, and electrons begin to flow. When charges flow, they generate a magnetic field curling around their path, just as described in Faraday's law of induction. Inside the Earth, there are no copper wires and simple bar magnets, but there is a huge reservoir of electrically conductive metal. Beneath the rocky mantle lies the core. At the very center is a solid inner core, but wrapped around it is a thick shell of molten iron and nickel called the outer core. Pressures and temperatures there are extreme. At its hottest, the outer core nears temperatures of around 6,000 degrees Celsius, similar to the surface of the sun, but the pressure is lower than in the inner core, so the metal remains liquid and able to move. Because it is hotter nearer the center and cooler closer to the mantle, the liquid metal in the outer core is constantly in motion. Hotter, lighter blobs of fluid rise upward. As they move into cooler regions, they lose heat and sink again. These overturning motions set up loops and swirls of flowing, conductive metal. Every loop of moving charges generates a little magnetic field. If each of these loops acted alone, the magnetic fields they created would point in many directions, canceling and reinforcing one another in a messy tangle. Instead, something helps organize them. The same Coriolis effect that bends winds and ocean currents also acts on the flowing metal in the core. As the Earth spins, Rising and sinking plumes of iron are twisted into spirals, like springs laid out along the direction of rotation. Each of these spiraling flows creates its own curling magnetic field. But because they are all aligned and twisted in similar ways, their individual fields add up. Inside the coils, the fields point mostly in one direction. Outside, they loop back around. The result, averaged over the whole planet, is a magnetic dipole. One large north magnetic pole and one large south magnetic pole, joined by a smooth field that emerges near one pole, stretches far into space, and returns near the other. It is an elegant outcome born from chaotic motion. Elegance does not mean stability, though. The dynamo is built from liquid metal, forever shifting. The flows that sustain the field are not fixed machines, but restless currents. As they subtly change, so does the field they generate. Tiny fluctuations ripple through it all the time. One of the clearest signs of this restlessness is the steady drift of the magnetic North Pole. Since the early 19th century, when explorers first measured its position with care, it has marched more than 1,100 kilometers away from its old location in northern Canada towards Siberia. In recent decades, its speed has increased from on the order of a few tens of kilometers per year to roughly 50+ kilometers per year. Seen on the time scale of a few human lifetimes, that movement looks like a wobble, like the slight unevenness in a spinning top that is still mostly upright. A reversal, by contrast, is a tumble. The entire pattern of the field rearranges so that the dipole points the other way. Geologists are confident that such full flips have occurred again and again. They have even counted them. The evidence lies frozen into rocks. When molten lava erupts onto the surface or spreads along the seafloor and begins to cool, tiny grains of iron-bearing minerals within it behave like compass needles. While the rock is still hot enough for those grains to move, they tend to align with the direction of the Earth's magnetic field at that time. As the rock cools and solidifies, the grains are locked in place, preserving a tiny record of the field's orientation. By sampling layers of volcanic rock and ancient ocean crust, scientists have found long bands where those mineral compasses all point one way, stacked between layers where they all point the other. The simplest explanation is also the most profound. Many times in the deep past, the entire magnetic field of the planet has flipped. On average, these magnetic flips seem to occur every few 100,000 years. Looking across many events, the gap often sits near 450,000 years, though the most recent reversals were separated by closer to 300,000 years. Set against that, it has now been about 750,000 years since the last full flip. It is tempting to say we are overdue. Yet when scientists read the long record stored in rocks and sediments, the timing does not reveal a steady beat. Some reversals bunch together. Others are separated by immense spans. In some eras, the field has flipped many times in quick succession. In others, it has held one orientation for tens of millions of years without changing at all, with gaps that can be so short in some ages and so long in others. It is hard to argue that there is any strict timetable we are meant to keep. What, then, actually triggers a flip? The details are still being explored. The leading idea is that small changes in the way the core flows and spins can, over time, disrupt the ordered spirals that sustain the present field. Heat moving in the mantle above may alter how the outer core cools. The slow growth of the solid inner core may nudge flow patterns. Whatever the mix of causes, the result is that the once coherent motion in the liquid metal breaks into something more tangled. The magnetic field, which depends on that motion, becomes patchy and irregular. During that transitional state, the field may sprout extra poles. Instead of a simple north and south, there might briefly be several north-like and south-like regions scattered across the globe. Lines of magnetic force twist and reconnect. Eventually, the flows organize themselves again into new spirals and a new dominant dipole. But which way that dipole points seems to be effectively random. Roughly half the time, the reformed magnetic North Pole ends up over what we now call the geographic South, and the field has reversed. This rearrangement is not quick in human terms. Evidence from the geological record suggests that a full transition can take anywhere from about 1,000 years to 10,000 years. During these passages, the overall strength of the field drops, in some cases, to perhaps only about 1/10 of its usual value. The invisible shield becomes easier for charged particles from space to pierce. In theory, that weaker shield could expose the Earth more directly to bursts of solar radiation and cosmic rays. Auroras, which now dance most often near the poles, might appear much farther toward the equator, coloring night skies but also signaling extra energy pouring into the upper atmosphere. On the ground, more high-energy particles could slightly increase the risk of certain cancers and other radiation-related illnesses. High above, satellites would be flying through harsher conditions. Their electronics could be damaged more often, shortening lifetimes and causing outages. Some researchers have suggested that these magnetic wobbles can shape life itself. A team in Sydney has pointed to a relatively brief weakening of the field known as the Lachamps event, tens of thousands of years ago, as a possible contributor to extinctions in Australia. That episode was not a full reversal, but what is called a geomagnetic excursion, a kind of partial, temporary collapse and recovery, lasting on the order of several hundred years rather than many thousands. In rocks and ice from that time, scientists see a spike in radiocarbon in the atmosphere, a sign that more high-energy particles were reaching the air and transforming nitrogen into radioactive carbon. The same period appears to line up with the disappearance of several large animal species on the Australian continent, including enormous wombat-like creatures known as Diprotodon and giant short-faced kangaroos called Procoptodon. The idea is that a weakened magnetic field led to climate shifts or increased radiation that helped push those animals past a tipping point. The evidence is intriguing, but far from simple. Across hundreds of millions of years, geologists do not find a clear pattern linking most magnetic reversals to global mass extinctions. Many flips seem to have come and gone without obvious harm to plants or animals. Even during the Lachamps excursion, the changes in Australia do not appear to have been echoed in the same way on other continents. That suggests a more complicated story, perhaps a perfect storm of local vulnerabilities and global changes, rather than a single cause and single effect. For human society, the timescales involved may be an unexpected comfort. Even at their quickest, these magnetic transitions unfold over many generations. That slowness would give us time to notice what is happening and adapt. If current satellites are too fragile under heightened radiation, we can design tougher ones. If solar storms become a greater threat to power grids, engineers can build in more safeguards and ways to isolate vulnerable components. And even in a weakened state, the magnetic field would not abandon us entirely. Above it all, the atmosphere itself is another layer of protection, scattering and absorbing much of the incoming radiation. It would take far longer than a few thousand years of weakened field for the atmosphere to be seriously stripped away. The ozone layer, which helps filter harmful ultraviolet light, does not vanish overnight. The more likely challenge is not instant doom, but a long, uneasy adjustment. That said, change on this scale rarely arrives without turbulence. Big shifts in how our technologies interact with the environment and in how we organize daily life are often bumpy, and we may already be living through the opening chapters of one of these magnetic stories. Measurements over the last couple of centuries show that the overall strength of the Earth's magnetic field has been slowly declining. Extrapolated in a straight line, that trend would take more than 1,000 years to bring the field close to zero, which leaves plenty of room for it to stabilize or strengthen again. It could be nothing more than a temporary wobble. At the same time, there is a particular region where the field is clearly weakened today. Over much of South America and the adjoining South Atlantic Ocean, the magnetic field dips and thins in what is known as the South Atlantic Anomaly. In that zone, satellites in low Earth orbit pass through an area of increased radiation. Some spacecraft automatically switch off sensitive instruments when they enter the anomaly to avoid damage. The Hubble Space Telescope, for example, pauses its observations each time it glides through that invisible patch of space. For people on the ground beneath, daily life continues as usual. The atmosphere still does its job. But for our machines in orbit, and for astronauts passing overhead, it is a reminder that the shield above us is not perfectly smooth. Since careful measurements began, the South Atlantic anomaly has slowly grown and shifted. To some scientists, this expansion hints that we may be witnessing either the early stages of another geomagnetic excursion, like the Lachon event, or one piece of the rearrangement that would accompany a full reversal. If such a transition does arrive, it is unlikely to be a single, world-ending moment. Civilization would not blink out in an instant, yet it would not be painless either. Some species might find themselves under new stresses. Technological systems would have to evolve. People would look up at nights, perhaps more often bathed in eerie curtains of light, aware that the sky is more restless than before. All of this can feel abstract when you step outside on a calm day and see only familiar blue overhead. Our magnetic field is invisible. You cannot touch it or hear it, and yet it shapes the way we have evolved, the way we build, the way we explore space. Learning that it has moods and cycles of its own is another reminder that even apparently solid parts of our world are in motion on their own timescales. Because a full collapse of the field has not happened yet, and because for now it remains strong enough to deflect most of what the sun throws at us, it is tempting to imagine that solar weather has little to do with our ordinary lives. Perhaps, you might think, apart from the slow dance of the Earth's orbit in Milankovitch cycles, the sun is just a steady lamp in the sky. But the star we orbit is not a static lantern. It is a restless sphere whose own cycles reach quietly into our days. If someone told you that the reliability of your technology or the warmth of a given year might be nudged by where the sun is in one of its repeating patterns, you might suspect they were drifting into astrology. Yet there is a small, solid truth hidden inside that old idea. Without assigning fates or fortunes, we can still say that as the sun moves through its own 11-year rhythm, some aspects of life on Earth shift with it. When that rhythm crests, there are more solar flares, more bursts of charged particles, more chances for subtle and not so subtle effects on our planet. The sun is our source of energy. Plants drink its light, animals eat the plants, and the chain continues upward until it includes us. Because that gift is so constant, it is easy to imagine the sun as changeless. It rises, arcs overhead, and sets day after day, and from our perspective, it looks the same. Peel back the glare, though, and a different picture emerges. With the right instruments to block the blinding direct light, astronomers have been able to look at the sun's surface in more detail for centuries. As far back as the early 1700s and before, careful observers with simple telescopes noticed dark patches drifting across the bright disk. These sunspots come and go. They are cooler regions, laced with intense magnetic fields, sometimes spanning tens of thousands of kilometers from edge to edge. The more we have learned, the more the sun has revealed itself as a boiling, shifting ocean of plasma, barely held in by its own gravity. In its core, temperatures climb to around 15 million degrees Celsius, hot enough that atoms are torn apart and fused into new elements, releasing immense amounts of energy. That energy works its way outward, and near the surface, bubbles and loops of superheated plasma rise and fall, twist and snap. Sometimes, the sun flings that energy outward in sudden flashes called solar flares, bright eruptions that bathe space in bursts of radiation. At other times, huge clouds of charged particles are hurled outward in coronal mass ejections, billowing through the solar system. The sun's atmosphere, or corona, which stretches far into space, is itself a strange place, somehow hundreds of times hotter than the visible surface below. It may look smooth from a distance, but it is one of the most active environments we know. What many people do not realize is that the sun's wildness is not constant. All that boiling, flaring, heaving motion rises and falls in strength, following a gentle rhythm that repeats again and again. The sun moves through a cycle that lasts about 11 years, gliding from a quieter phase, called solar minimum, into a livelier phase, called solar maximum, and then easing back down. During the high part of this cycle, dark sunspots bloom more often on its surface. Solar flares flash more frequently, and great clouds of plasma called coronal mass ejections are flung into space with greater regularity. Compared to the calm of solar minimum, you are many times more likely to see a strong flare when the sun is near its peak, and large eruptions that might happen only every few days can suddenly arrive several times in a single day. Astronomers call this repeating pattern the Schwabe cycle. It is one breath inside a larger motion known as the Hale cycle, which tracks the way the sun's magnetic field flips. With each new Schwabe cycle, roughly every 11 years, the magnetic north and south on the sun swap places. Over the next cycle, they swap again, returning the field to its original orientation. Taken together, those two beats make one full magnetic heartbeat. Tick, tick, tick. This slow metronome of rising and falling solar activity ripples outward through the solar system. Even though we cannot feel it directly on our skin, the Earth and everything on it moves in quiet step with that rhythm. The sun's inner workings are still full of mysteries, and we do not yet know exactly why this particular cycle lasts about 11 years instead of 9 or 20. The pattern is clearly tied to the twisting and tangling of magnetic fields inside the sun, but the deeper cause of its timing remains out of reach. Because of this uncertainty, some researchers have looked outward for hints, noticing that Jupiter, the largest planet in our system, takes almost exactly the same amount of time to circle the sun once. It is tempting to imagine that the tug of Jupiter's gravity somehow sets the clock of the solar cycle. Jupiter is massive, outweighing all the other planets combined many times over, and it certainly pulls on the sun as they orbit a shared center of gravity. Yet, so far, that link has not explained the way the solar cycle rises and falls, nor the fact that its strength and length wobble from one 11-year span to the next. Whatever drives the sun's rhythm seems to come mostly from within. While the heart of the cycle hides inside the sun, its effects are easier to see in the space around us. Modern civilization has climbed into orbit. Satellites carry signals, images, and data. Space stations house people for months at a time. Space weather is now as real a concern as storms at sea once were for early sailors. When the sun hurls bursts of energy and particles toward us, they can buffet the invisible magnetic bubble around the Earth and stir up what we call geomagnetic storms. The good news is that we are not entirely at their mercy. Spacecraft between the Earth and the Sun keep watch, measuring the solar wind and giving us warning when a large burst is on its way. That warning can be a matter of days. With that time, astronauts can move into better shielded parts of their stations, and mission controllers can put satellites into safer modes, powering down vulnerable electronics. High-energy particles streaming from the sun can induce unexpected currents in wires and circuits, pushing systems beyond what they were designed to handle. Turning them off or into standby can mean the difference between a brief interruption and permanent damage. But the sun's temper does not stop at the edges of machines. When a strong geomagnetic storm sweeps over the Earth, it can gently heat the upper atmosphere. That heating makes the atmosphere puff outward, expanding into regions of space that are usually nearly empty. Satellites in low Earth orbit normally feel only the faintest whisper of drag from the thin air at their heights and need to adjust their paths with small bursts of fuel only occasionally. During and after a geomagnetic storm, that whisper becomes a noticeable tug. In those times, satellites that circle close to the Earth may find their orbits decaying more quickly. Instead of making tiny course corrections a few times a year, operators might need to fire thrusters every few weeks to keep them from sinking too low. If a storm is particularly strong and a satellite's fuel is nearly spent, that extra drag can be enough to pull it out of the sky sooner than planned. In the late 1980s, one especially powerful geomagnetic storm swelled the atmosphere so much that a satellite devoted to studying solar flares itself was slowed beyond rescue and re-entered the atmosphere. It is a quiet irony. The sun, through its storms, can knock down the very eyes we use to watch it. Organizations that track objects in orbit must also scramble when space weather turns rough. Each geomagnetic event jostles satellites out of their old paths a little. Afterward, ground stations have to search, measure, and update the positions of hundreds of objects, rewriting the maps used to avoid collisions. It is as if, after a single night of heavy wind, someone had gently moved every buoy in a harbor. Closer to us, solar storms can reshape layers of the atmosphere that carry and bend radio waves. The ionosphere, a region filled with electrically charged particles, can grow denser and more disturbed under the impact of incoming energy. For systems that rely on precise timing, like global positioning satellites, those changes can act like a shifting lens, briefly bending signals in unexpected ways. A navigation system that is usually accurate to within a meter can suddenly be wrong by several meters. On the ground, long power lines and transformers feel the sun's reach in yet another way. Geomagnetic storms can induce weak but widespread currents in the crust and in long metal conductors. Power companies watch the solar cycle and brace themselves for the busier years, adding monitoring and safeguards so that extra currents do not quietly overheat equipment or trigger cascading failures. High-frequency radio users, from amateur operators to airline pilots, can find their usual communication channels dimmed or cut off as the ionosphere's reflective properties change. Signals that once bounced neatly over the horizon may be absorbed or scattered. Sometimes, though, The same charged layers can carry signals far beyond their normal range, letting radio hobbyists exchange whispers across oceans by skipping their transmissions off the sky. Taken together, these effects match some of the little predictions in our playful horoscope. As the sun heads towards solar maximum, technology becomes just a bit less reliable. Minor glitches and flickers align with times when the sun is more active. The next peak is expected around the middle of this decade, and scientists and engineers are quietly preparing for a busier space weather season. There are, of course, beautiful side effects as well. When bursts of charged particles from the sun funnel down along the Earth's magnetic field lines and collide with atoms in the upper atmosphere, they can light the sky in curtains of green, red, and violet. These auroras are usually confined to high latitudes, but during strong solar storms they can spill farther toward the equator. People in places like Canada, Scotland, or the northern United States may see the northern lights far more often near solar maximum. For aurora chasers, the stormy years of the sun are a gift of shimmering nights. It would be easy to stop the story here, to say that the sun's cycles mainly play with machines and the upper air. Yet nature has a way of knitting everything together. There are hints, still being explored, that solar cycles may reach into the lives of plants, animals, and even our own bodies and minds. Some of these connections are gentle and indirect. When the sun is at solar minimum, its outflowing solar wind is slightly weaker. Our planet's magnetic bubble then deflects fewer of the high-energy particles arriving from outside the solar system, known as cosmic rays. More of those particles reach the upper atmosphere, where they collide with air molecules and sometimes help seed the formation of clouds. One idea, still debated, is that this could subtly shift cloudiness and, with it, weather patterns. During solar maximum, by contrast, the increased activity of the sun can raise global average temperatures by a small amount, less than about half a degree Celsius. The Earth's climate does not spin out of control because of this. Once the cycle wanes, temperatures ease back. But for creatures that pay close attention to seasonal warmth, even a small nudge can matter. In warmer years, some birds have been observed laying their eggs earlier in spring, adjusting their timing to match the availability of food for their chicks. Humans, too, may feel the sun's pulse in ways we are only beginning to untangle. Medical records and large population studies hint at tiny correlations between solar activity and certain health statistics. One study that followed hundreds of thousands of people over many years suggested that some illnesses showed small peaks in occurrence shortly after solar maximum. Other work has hinted that those born during periods of especially high, chaotic solar activity might face a slightly higher risk of some mental disorders later in life. If the link is real, it would mean that the state of the sun at the moment of your birth could leave a faint fingerprint on your nervous system. It is not astrology in the traditional sense, and the differences are very small, but it is an intriguing reminder that we live in a larger environment than we usually imagine. It is important to remember how gentle these influences are. As one scientist put it, the signals are so faint that you need many thousands of patients to see them emerge from the noise. Whatever the sun is doing, its cycles do not rule our fates. They are background music, not a conductor. They should not keep anyone from going about an ordinary life under the sky. As this story is being told, the sun is once again climbing toward a solar maximum, expected around the middle of the decade. For those worried about flares and storms, there is a softer way to look at it. High activity may slightly increase certain risks, but it may also encourage resilience. Some have speculated that bursts of radiation and subtle environmental stresses could, over the very long term, have nudged life on Earth toward greater creativity and adaptability. It is humbling to think that, perhaps in some distant age tens of thousands of years ago, a human brain first took a leap toward abstract thought and self-awareness under a restless sun near its peak. If so, we might owe part of our ability to wonder about the universe to the very cycles we are now learning to measure. The same solar storms that complicate our technology may have helped, in some small way, to make us who we are. And while the sun's reach is vast, it is not alone in shaping our world. Another companion moves around the Earth more quietly, its pale face rising and setting with a softer rhythm. The moon tugs at our oceans, guides tides, and whispers into the lives of countless creatures. Its orbit, too, has cycles written into it, including one that, every 18 and a bit years, gently shifts the way its gravity and the sun's combine. When that happens, high tides grow higher still, nudging coastal waters toward their limits. In that slow turning, we arrive at yet another of Earth's repeating patterns. The moon's quiet rhythm that matters here has a formal name: the lunar nodal cycle, sometimes called the precession of the lunar nodes. Beneath that technical phrase is a simple picture. You probably know that it takes about 29.5 days for the moon to complete one full orbit around the Earth. But that path is not laid perfectly flat on the same plane as the Earth's orbit around the Sunday. Instead, the moon's track is tilted by about 5 degrees from the ecliptic plane, the thin, imaginary sheet along which our planet circles the Sunday. Because of that tilt, the moon spends part of each month a little above that plane, and part of the month a little below it. Twice in every orbit, it crosses the ecliptic, once heading upward and once heading downward. Those crossing points are called the nodes. An ascending node where the moon moves from south to north of the ecliptic, and a descending node where it moves back from north to south. These nodes are not fixed in space. Over about 18.6 years, they slowly creep backward around the Earth, completing one full lap. That slow drift is the lunar nodal cycle. The nodes themselves are what quietly change our tides. To see why, it helps to revisit how tides work. The moon's gravity pulls on the Earth, and because water can flow, the oceans respond more strongly than rock. On the side of the Earth facing the moon, water is drawn toward it, rising into what we call a high tide. Less obvious is the second bulge on the far side of the planet. That one is not driven directly by the moon's gravity, but by the shared dance of Earth and moon around their common center of mass. As they spin together, like two partners holding each other's hands and turning, the water on the far side has a tendency to continue in a straight line, lifting away slightly in a second high tide. The sun also tugs at our seas. Its gravity is stronger overall because its mass is so vast, but it is also very far away, so the difference in its pull from one side of the Earth to the other is smaller. The sun's tidal effect is roughly 1/3 as strong as the moon's. When the sun, moon, and Earth line up, their tidal pulls reinforce one another, and we experience especially high and low tides, known as spring tides. These are not named for the season, but for the way the water seems to spring higher several times a year. As the geometry lines up, spring tides quietly arrive. When the sun and moon are at right angles, their pulls partly cancel, and the range between high and low tide shrinks. Those gentler swings are called neap tides. Now imagine adding the nodes into this picture. During a spring tide, the sun and moon are already working together along roughly the same line, drawing water into exaggerated bulges, but the alignment is not always perfect. Most of the time, even when they are pulling in broadly the same direction, the moon's tilted orbit keeps it a little above or below the best possible line. Only when the moon is crossing the ecliptic at a node do the Earth, Moon, and Sun line up in a way that makes their combined influence as strong as it can be. During parts of the nodal cycle, the geometry is such that the Sun and Moon are better positioned to reinforce one another when the Moon passes through its nodes. In the middle of each 9.3-year half of the cycle, their tidal pulls are not quite so perfectly in step, and tides are more moderate. But when a node, the Sun, and the right phase of the Moon all conspire, spring tides become even more extreme. Water reaches just a little higher on beaches and seawalls, and the background risk of flooding quietly rises. The last time this alignment drew widespread attention was in the late months of 2015. Agencies in both the United Kingdom and the United States issued warnings ahead of especially high tides, asking coastal communities to be cautious. In September, some minor flooding arrived, mostly manageable. The real trouble came later, when heavy rains happened to fall on top of those elevated tides. In October, parts of South Carolina experienced flash floods that damaged homes and roads and forced rescues by emergency services. Toward the end of December, the United Kingdom faced some of its worst flooding in a century. Storm Desmond swept in with intense rain, and when that rain met already swollen rivers and raised sea levels, the result was devastating. Towns flooded, defenses failed, and the damage was counted in lives disrupted and in an estimated £1.3 billion in losses. Even that, serious as it was, came from a nodal alignment acting on top of roughly 20th century sea levels. The concern looking ahead is that the next time the lunar nodes line up with the Sun in a similar way, the stage will be different. Over the past 100 years, the average level of the oceans has been rising, driven primarily by human-caused warming, melting ice sheets, and the slow expansion of seawater as it warms. When you lift the baseline, every extra push from tides starts from a higher step. The next particularly important part of the nodal cycle arrives in the mid-2030s. Studies led by teams focused on sea level change suggest that for many coastlines, especially around the mainland United States, Hawaii, and Guam, this combination of higher background, sea level, and stronger tidal swings could lead to a sharp jump in the number of coastal floods. Some projections suggest that minor flooding events, the kind that might happen a few times a year now, could become several times more frequent from one decade to the next. Even if each individual flood is small, the cumulative effect can be large. Roads, storm drains, and buildings are rarely designed with the expectation of being regularly doused in salt water. Increased flooding can damage foundations, corrode infrastructure, and stress already aging systems for electricity, drinking water, and sewage. After floodwaters recede, they can leave behind pockets of standing water in low-lying places. Those stagnant pools are ideal breeding grounds for mosquitoes, which can carry diseases like malaria or dengue fever. Floods can also spread waterborne illnesses such as hepatitis A and cholera when they contaminate drinking water or overwhelm sanitation. There is an economic shadow as well. As floods become more common, insurance for coastal properties can grow more expensive or vanish altogether. Homes and businesses that once seemed safely and permanently rooted may suddenly be seen as risky investments. Property values can fall, and communities that have lived for generations with the sea at their doorstep may find staying there increasingly difficult. The lunar nodal cycle does not just affect humans. It reaches into other living systems that hug the edges of land and sea. Salt marshes are one example. Flat, grassy wetlands that are regularly flooded by tides. They serve as nurseries and feeding grounds for countless small creatures, especially invertebrates like worms, crabs, and snails. These, in turn, support fish, seabirds, and many other animals higher up the food chain. Some estimates suggest that about 3/4 of fish species important to fisheries spend at least part of their lives in or near such habitats. When high tides climb higher than usual, especially if they do so often, salt marshes can be drowned. The plants that hold the sediment in place cannot survive constant submersion, and the structure of the marsh begins to break down as the habitat erodes or disappears. The invertebrates that relied on it suffer, and so do the birds and fish that depended on them. The effects ripple outward, touching ecosystems offshore and inland. Yet even in this sobering picture, there are places where the moon's quiet wobble brings more mixed news. Mangrove forests, for instance, seem to respond strongly to the nodal cycle in ways that can be beneficial. Along many tropical and subtropical coasts, mangroves stand like guardians, trees with tangled above-ground roots that anchor the shoreline and create sheltered mazes for young fish and other marine life. Analyses of mangrove cover across much of Australia have shown that the lushness of these forests ebbs and flows with the lunar nodal cycle. When the nodal influence is at a minimum and tides are less extreme, some mangrove areas become relatively dry, the canopy thins, and the forest retreats slightly. When the nodal cycle reaches its peak and high tides run higher, water reaches farther inland and stays longer in the intertidal zone that mangroves prefer. The trees respond with fresh growth, and the canopy expands. In these phases, mangrove ecosystems can flourish. That flourishing matters far beyond the trees themselves. Mangroves are among the most effective natural defenses against coastal erosion and storm surge. Their dense roots and branches slow incoming waves, robbing them of height and energy before they reach inland areas. They also soak up carbon dioxide at remarkable rates, storing several times as much carbon per unit area as many rainforests. In this way, they help buffer both the rising seas and the changing climate that contributes to those rises. Because a band of mangroves can so effectively calm waves, their preservation and restoration are powerful tools for living with the lunar nodal cycle rather than constantly fighting it. Studies suggest that a strip of dense mangrove forest only about 100 meters wide can cut the height of an incoming wave in half. In sparser forests, where trees and roots are spread farther apart, the same reduction in wave height might require 500 meters of distance. The message is clear. Well-kept, healthy mangroves are strong shields. They are not the only path forward. In some places, the best response may be to work even more deliberately with water, as some low-lying countries have done for centuries. The Netherlands, for example, has large areas that already sit below sea level, with others at constant risk of flooding. Over generations, the people there have learned to shape their infrastructure to accommodate water rather than simply wall it off. One of their tools is the polder, land reclaimed from the sea or rivers and surrounded by dikes. Within a polder, a network of canals and pumps carefully manages water levels, moving excess water back out to sea or into rivers before it can rise high enough to spill over. Homes, farms, and factories can exist on these protected patches of land because their relationship with water is actively managed. Dams, strengthened dunes, and other layered defenses complement this system, all built on the understanding that water will always be nearby and must be guided. not ignored. Looking at such examples, it becomes easier to imagine a future where coastal communities adapt thoughtfully to the moon's cycles, protecting and restoring natural buffers like salt marshes and mangroves, building flexible and intelligent infrastructure, and planning with these rhythms in mind can soften the blows that might otherwise come as a surprise. The harder truth is that the moon, serene as it appears in the night sky, exerts a quiet power over our shores. When its orbit, its nodes, and the rising seas all line up just so, that power can overwhelm walls, roads, and plans that were built for a calmer past. But there is comfort in knowing that the same cycles that challenge us also give us time. The nodal rhythm is not sudden. It moves in decades, not days. With knowledge, we do not stand entirely helpless beneath it. Understanding how and when these higher tides arrive lets us prepare, rethink where and how we build, and look to nature for allies. In that way, even as the moon's distant pull threatens to test our coasts, our awareness of its patterns becomes a kind of counterweight, a quiet strength we can use to shape gentler futures along the edge of the sea. If we are to live through what is coming, it feels more important than ever to lean into that quiet, stubborn creativity that humans are so good at, to adapt, to listen, to work with our planet instead of forever pushing against it. Most of what we have been whispering about so far has been made of deep cycles and hidden mechanisms, orbits, tides, winds, the slow churning of molten metal. But above all of that, there is another kind of moment where the sun and the moon briefly speak together in a different language. When it happens, the world itself seems to pause. Birds fall silent, shadows sharpen, daylight cools into a strange, silvery twilight, and hearts all over the path of darkness lift in the same breath of awe. A total solar eclipse is a simple thing on paper. One object passes directly in front of the sun and hides it completely from view. In our case, it is usually the moon that does the hiding, slipping into just the right position in its orbit so that, from a narrow strip on the Earth's surface, the sun is fully covered. One such eclipse swept across parts of North America in April of the year 2024, and many people traveled long distances just to stand for a few minutes beneath its shadow. What makes an eclipse here on Earth so special is a quiet coincidence of size and distance. The sun is enormous, roughly 1.4 million kilometers across. The moon is tiny by comparison, only about 3,400 kilometers wide. And yet, because the sun is so far away and the moon is so much closer, their apparent sizes in our sky, their angular diameters, are almost exactly the same. The result is a kind of cosmic perfect fit. The moon can cover the bright disk of the sun so neatly that only the sun's outer atmosphere, the corona, remains visible. The corona is usually too faint to see against the glare. During totality, it becomes a delicate, ghostly halo, stretching hundreds of thousands of kilometers into space. Around the dark circle of the moon, streamers and feathers of pale light reach outward. Along the edge, if you look carefully through a safe telescope, you can see the jagged outline of the moon's craters cutting into that glow. Here and there, reddish arcs and knots rise from the sun's limb. These are prominences, loops of charged particles held aloft by intense magnetic fields, each one made of millions of tons of hot plasma. On the ground, the moon's shadow carves out a narrow path across the planet. The darkest part, where the sun is completely hidden, is called the umbra. It is only on the order of a couple of 100 kilometers wide, roughly 250 kilometers or so, and it races across the surface as the moon moves along its orbit. During the April eclipse, This shadow first touched the west coast of Mexico, then swept northeast across the United States, and finally slid over parts of Canada before heading back out over the ocean. From space, satellites have watched that shadow run along the Earth at roughly 1 kilometer every second, a moving pool of night against the lit face of the planet. The shadow is not a knife edge. Around the umbra lies the penumbra, where the moon covers only part of the Sunday. Under the penumbra, the light dims, but never fully dies. The shape and softness of that shadow are set by the sizes of the sun and moon, and the distances between all three bodies. You might wonder why. If the moon orbits the Earth roughly once every 29.5 days, we do not get an eclipse every month as it crosses in front of the Sunday. The reason is geometry again. The moon's orbit is tilted by about 5 degrees relative to the plane of the Earth's orbit around the Sunday. Most months, when the moon passes between us and the sun, it is a little above or below the exact line needed to block the light. Only a few times a year does everything line up just right, with sun, moon, and Earth arranged almost perfectly in a straight line. Astronomers have a word for this three-body alignment: syzygy, a small, strange word for a very beautiful thing. For those who experience totality, the emotional weight of it can be surprising. The light shifts through colors it never usually wears. Shadows look wrong, the temperature drops, and familiar places feel briefly alien. Many people come away from their first eclipse with the sense that they have witnessed something quietly profound, a demonstration of just how precisely our celestial neighbors can align. And yet, even eclipses are part of a wider pattern. They are not random miracles, but the visible tip of an orderly dance. That dance matters because it reminds us that the Earth sits inside many cycles at once. The tilt and shape of its orbit, the slow nodding of the moon, the rhythms of the winds and oceans, the pulsing of the sun, the turning of molten iron far below. These cycles shape climate and weather over timescales from days to tens of thousands of years. Once we understand them, they give us context. They help explain why ice ages wax and wane, why certain years bring more storms, why some coasts face unusually high tides. They let us say, with some confidence, when floods are likely to be worse, when droughts may linger, when calm is likely to return. But when we set all of those natural rhythms side by side with what is happening to the Earth's temperature now, something feels out of place. The pattern of the present does not sit comfortably on top of the patterns of the past. The planet is warming. That is not news anymore. What is less often talked about is how this recent warming compares to the huge swings Earth has already lived through, and how we know. We are used to hearing about global warming as a snapshot. Today's temperatures, this decade's heat waves, this century's graphs. The deeper question is one of context. Are we seeing just another rise in a long series of natural rises and falls, or are we watching something that breaks the usual rhythm? To answer that, we have to ask a deceptively simple question. What did the temperature used to be? Measuring the present is the easy part. Put a thermometer in the air, and it will tell you the local temperature. Scatter enough measurements around the world, on land and sea, and you can calculate an average for the whole planet. Scientists have been collecting such readings in a systematic way since the middle of the 19th century. That gives us about a century and a half of fairly detailed, direct observations. Before that, mercury thermometers themselves only appeared in the early 18th century. Beyond that point, no one was standing in a field or on a ship's deck writing down temperatures. And yet, we still speak of climates from thousands, even millions of years ago. We cannot travel back, so we rely on the traces the past has left inside ice, rock, and the shells of once living things. In very cold places, such as the heart of Antarctica or Greenland, snow that falls in winter does not fully melt in summer. It accumulates year after year. The weight of new snow compresses the old layers beneath, turning them slowly into ice. As each layer forms, it traps tiny bubbles of air from the atmosphere of that year, like countless small time capsules. Drilling down through these layers gives us ice cores, slender cylinders of ice that can be read like a tree's rings. In the laboratory, scientists slice these cores and gently melt specific layers, releasing the ancient air. By measuring the relative amounts of gases in those bubbles, such as carbon dioxide, oxygen, and others, they can infer how much heat the atmosphere of that time was likely able to trap. We know from experiments how different gases behave when they are warmed. Carbon dioxide holds onto more heat, while oxygen and nitrogen hold less. Combining that knowledge with many samples taken from many depths, researchers can reconstruct a rough record of global temperature across the span of hundreds of thousands of years. Ice, however, can only carry us so far. Even the oldest glaciers are on the order of 1 million years old at most. The Earth's story stretches back much further. To follow temperature back across tens or hundreds of millions of years, scientists turn to the remains of tiny sea creatures called foraminifera. Foraminifera are single-celled organisms that live in the oceans. Many of them build delicate shells around themselves from minerals dissolved in seawater. These shells, though tiny, often no larger than a speck of dust, record something important. As they form, they incorporate oxygen from the surrounding water. That oxygen comes in slightly different forms, or isotopes, and the ratio between those isotopes depends partly on the temperature of the water at the time. When foraminifera die, their shells drift down to the seafloor and can become part of the sediments there. By drilling into ancient ocean beds and collecting these fossil shells from different depths, scientists can measure the oxygen isotopes locked inside. From that, they infer the temperature of the oceans when those shells were formed. Because foraminifera have existed for roughly 500 million years, they offer a way to sketch the broad strokes of climate across almost that entire span. The picture that emerges from these tiny witnesses is a restless one. Over the last 500 million years, the average global temperature has swung dramatically. There have been times when the Earth was, on average, perhaps 14 degrees Celsius warmer than it is today, with steamy forests near the poles and little or no permanent ice. There have also been eras when the average was several degrees cooler than now, with ice sheets spreading farther from the poles. Our present climate sits somewhere in the middle of that long range. On such vast scales, the patterns are hard to tease apart. Some shifts seem linked to the slow rearrangement of continents as tectonic plates drift. When land masses cluster near the poles, it is easier for ice sheets to grow and persist. Volcanoes, too, can play a role, pouring carbon dioxide into the atmosphere over long stretches of time and gently nudging temperatures upward. Impacts from large asteroids can darken the sky for years, cooling the surface and disrupting climate in sudden jolts. Life itself has also left its mark on the thermometer. Around 450 million years ago, plants began to spread widely over land. As they grew and flourished, they drew carbon dioxide out of the air and locked it into their tissues and eventually into soils and rocks. With less carbon dioxide available to trap heat, the planet cooled. Other evolutionary leaps, the rise of great forests, the spread of plankton in the seas may likewise have shifted the balance, sometimes warming, sometimes cooling, over spans of millions of years. Through all of this, the Earth has responded to slow, natural pushes. Temperatures have gone up and down, sometimes sharply, but on timescales measured in hundreds of thousands or millions of years. Against that backdrop, the rapid rise in global temperature over just the last century stands out like a sudden, steep spike on a long, rolling line. However, this is not the full picture. By gently increasing the resolution of that long climate record and zooming in, another pattern begins to appear. If we focus on the last, roughly 65 million years, the giant swings smooth out into a landscape of smaller hills and valleys. Look closer again, and more detail emerges. With each step inward, the line of temperature stops looking like a single wavering curve, and instead reveals repeating shapes, brisk rises, followed by slower descents, up and down, again and again. Each of those long, slow dips represents not just a cold spell, but an entire ice age. In technical terms, an ice age is any period in which permanent ice exists at the poles. That is not always true in Earth's history, which means that, strictly speaking, we are living inside an ice age right now. Within that broader icy era, though, the climate pulses. Great sheets of ice advance and retreat. At times, during the last full glacial peak, those ice sheets reached as far as what is now the United Kingdom and pushed deep into parts of North America. The rises and falls riding on this background match the quiet pull of the Milankovitch cycles, changes in the shape of Earth's orbit, the tilt of its axis, and the wobble of that tilt over time. Some of these cycles take on the order of 23,000 years, some around 41,000 years, some roughly 100,000 years, and others stretch out to hundreds of thousands or even a few million years. When their cooling phases line up, summers grow slightly weaker at high latitudes. More winter snow survives the melt, and ice begins to spread. If we zoom one step further toward the present, we find ourselves on a kind of ledge in this landscape. After rising out of the last deep glacial phase, global temperatures have hovered in a relatively gentle plateau. This is the interglacial period we live in now, a pause of many thousands of years in which the world is warmer than during a full glaciation, but still cool enough to keep ice anchored to Greenland and Antarctica. Human history, from the first settled villages and the earliest agriculture, to pyramids, cities, and modern nations, unfolds entirely on this plateau. Before it, humans existed, but our species had not yet learned to build the kinds of complex civilizations we now take for granted. Scientists call this warm stretch the Holocene. For much of it, temperatures bobbed a little up and down, but stayed within a fairly narrow band. Right at the end of the graph, though, a small hook curves sharply upward. That hook represents about 1 degree Celsius of warming. On its own, 1 degree does not sound dramatic. Past interglacial peaks have reached similar average temperatures. What makes this rise stand out is not its height, but how abruptly it climbs. Almost all of the wiggles and swings visible in the earlier parts of the record took place over spans of thousands to millions of years. Even the steeper climbs, when inspected closely, represent slow-motion changes from the point of view of a single human lifetime. By contrast, the recent uptick compresses a comparable change into roughly 1 century. For ecosystems, that is a blink. The usual suspects: orbital cycles, subtle shifts in the sun's output, the long wobble of the moon's orbit simply do not move that quickly. Milankovitch cycles are gentle sculptors, wearing down climate over vast ages like water carving stone, not like a hammer blow in a single human century. When we magnify sections of the past where the temperature appears to jump, the detail almost always reveals that those jumps unfold over at least a few thousand years. Nor have we seen any obvious cataclysm like the impact that contributed to the end of the dinosaurs. That ancient object is thought to have been on the order of 10 kilometers wide, and to have slammed into the Earth with the energy of billions of Hiroshima-scale bombs. It threw dust and aerosols into the sky, blocked sunlight, and rearranged climate in a geological instant. If something like that had happened since the middle of the 1800s, we would not be speculating about it. We would remember El Niño and La Niña. Solar cycles and other shorter-term patterns are also well enough understood to be folded into our models. Their warming and cooling effects add ripples to the line, but they cannot explain the sustained, global rise we have seen. When all the known natural cycles are accounted for, one factor remains that matches both the timing and the size of the change: us. Life reshaping climate is not a new story. Long before humans appeared, other organisms altered the planet in ways that affected temperature. When plants spread widely on land hundreds of millions of years ago, they drew carbon dioxide from the air and released oxygen, likely contributing to a cooling trend. Much earlier still, tiny cyanobacteria learned to harvest sunlight through photosynthesis and began venting oxygen into an atmosphere that had very little of it. That great oxidation event transformed the air and may have helped trigger a near-global freeze, sometimes called Snowball Earth, when glaciers reached almost to the equator. The lesson in all of this is that the balance of gases in the atmosphere is delicate. Change it enough, and the climate follows. A single kind of organism, given time and reach, can overwhelm the slow background of orbital cycles. Since the start of the industrial era, humans have become that organism. Around the late 1700s, we began burning coal, then oil and gas on a massive scale. We cleared forests, plowed vast fields, and built an industrial civilization whose waste products include large quantities of greenhouse gases. Since about 1850, measurements show that carbon dioxide and methane in the atmosphere have climbed far beyond the levels seen in ice cores covering the last 800,000 years, a span that includes multiple ice ages and interglacials. Carbon dioxide now sits at around 410 parts per million, and methane at around 1,866 parts per billion, both higher than any values found in those ancient bubbles of trapped air. Each of the last 4 decades has, on average, been warmer than the ones before it in the instrumental record. Extra heat does not just sit politely in the air. It moves through systems, changing the way water, ice, soil, and living things behave. One of the clearest examples of this is in the behavior of fire. Much of the planet's carbon is stored not in the atmosphere, but in the ground, in the deep ocean, and in living biomass, trees, grasses, plankton, animals. When vegetation dries under prolonged heat and drought, it becomes easier to ignite and harder to extinguish. Fires that once were rare or limited can become larger, more frequent, and more intense. Across the high northern latitudes stretches a vast belt of forest, known as boreal forest or taiga, running through Canada and Russia. It is the second largest biome on Earth after the oceans, made up mostly of coniferous trees. In the year 2014, a series of fires swept through parts of the boreal forest in Canada's Northwest Territories, burning an area roughly the size of the state of Maryland, on the order of 7 million acres. Those fires alone released close to 100 million tons of carbon into the atmosphere, roughly half as much as all the plants in Canada usually absorb in a year. Events like this feed a feedback loop. The more carbon dioxide we place in the air, the warmer and drier some regions become. The warmer and drier they are, the more likely and severe fires become. The more forests and peatlands burn, the more carbon is returned to the atmosphere. At present, biomass burning, the burning of forests, grasslands, and other vegetation accounts for a significant fraction of global carbon dioxide emissions, and in some high-latitude regions, the trend points toward more fire, not less. When a forest burns, it does not grow back overnight. Young trees take decades to reach the size and density needed to store as much carbon as the old forest did. In Yellowstone National Park, for example, large fires in 1988 scorched more than a third of the park. Even after 20 years, less than a third of the burned area had regained full forest cover. During that regrowth, the land's capacity to pull carbon from the atmosphere and hold it safely is diminished. The Australian bushfires of the southern summer of 2019 into 2020 offered a stark, visible reminder of how far the effects of such events can reach. By the end of December, plumes of smoke from burning forests and scrublands were large enough to be clearly seen from orbit. Against the white of weather clouds in satellite images, the smoke showed as brown and gray streaks. Day after day, the fires continued, their glow lighting the night and their smoke darkening the day. On some days, the smoke streams stretched thousands of kilometers over the Pacific Ocean. Winds shifted and carried it southeast, draping a heavy veil over New Zealand and turning its skies an eerie color. Cities like Sydney sat under a blanket of haze that stung lungs and reduced visibility. For a time, air quality there ranked among the worst in the world. In the days that followed, the smoke did not simply vanish. It continued to circle, thin and spread, a diffuse reminder high in the atmosphere of what had burned below. All of this is part of the same story. A rapid rise in temperature, unlike the usual slow pulses of the past, driven not by distant orbital mechanics or ancient volcanic shifts, but by the choices of a single, clever species living on the surface of a small, blue world. Wildfires are a natural part of life in places like Australia, but the fires that burned there in the closing months of 2019 and the beginning of 2020 were something different. In scale, intensity, and impact, they stretched beyond anything recorded before, and they are only one piece of a larger pattern. Around the world, the area covered by surface ice has been shrinking steadily since the middle of the 20th century. When scientists look back across the last 2,000 years, they do not find another period quite like this, with glaciers and sea ice retreating so consistently in so many places at once. As that ice vanishes, another quiet feedback begins to work. Ice is bright. It reflects a large fraction of the sunlight that falls on it back into space. Darker surfaces, like open ocean or bare rock, absorb much more of that light as heat. When white ice is replaced by dark water or soil, the planet warms more easily. That extra warmth melts more ice, revealing more dark surface, and the cycle continues. It is like pushing a cart down a slope. Once it is moving, it has a momentum of its own, unless something slows it. Rapid shifts in temperature make life's usual ways of adapting much harder. Over long stretches of time, species can slowly evolve traits that suit new conditions. It took thousands of years for cold-adapted creatures of the last glacial period, like woolly mammoths, to give way to animals better suited to warmer climates. like modern elephants. Natural selection works on the scale of many generations. When the environment changes as quickly as it is changing now, there is less time for that slow adjustment. Faced with a climate that is warming in decades rather than millennia, living things have only a few options. They can move. If there is somewhere cooler or wetter to go, they can adjust their behaviors within the limits of their physiology. Or they can fail, as the zones that feel comfortable for many plants and animals drift poleward or climb up mountainsides. Some habitats simply disappear. New, hot, dry regions can spread where there were once forests or grasslands, and many forms of life are poorly prepared for those conditions. It is important to remember that none of this is fated. The climate system has inertia, but it is not an unstoppable runaway. If we slow and eventually stop adding greenhouse gases to the air, the imbalance will ease. Over time, the gentler, natural cycles, the slow turning of Milankovitch rhythms, the background breathing of the planet will take over again, and the sharp upward spike will flatten. That is why so much effort has gone into understanding what is happening and into advising those who make decisions. Groups like the Intergovernmental Panel on Climate Change, a worldwide collaboration of scientists supported by many governments, have been working for decades to assess what the evidence shows. In their 6th major assessment of the physical science, published in the early 2020s, they wrote that it is unequivocal that human influence has warmed the atmosphere, the ocean, and the land. That word is a careful one. It means that when all the lines of evidence are set side by side, the conclusion is no longer in serious doubt. Alongside that stark statement, they also sketch out paths forward. A central theme is the need to bring net emissions of carbon dioxide down towards zero, because that gas is the largest driver of long-term warming, with methane and a few others close behind. In addition to reducing how much we emit, they suggest that we will likely need ways to remove some carbon dioxide from the air and store it elsewhere. A few projects of that kind already exist in the real world. Some, like the ones in Norway, that aim to pump captured carbon dioxide into depleted fossil fuel reservoirs beneath the seabed, are early examples of what might one day be done at larger scales. Whether these technologies will grow fast enough and work reliably enough is still an open question. For now, they are experiments with promise and limits, not magic solutions. Any serious response will probably need both deep cuts in emissions and, where it makes sense, careful use of carbon removal to help pull the system back toward balance. Stepping back, one of the reasons to place our present moment into the context of Earth's long history is to clarify exactly what is and is not unusual. It is true that the planet has been hotter than it is now. It is true that ice sheets have come and gone, sea levels have risen and fallen, and climates have shifted dramatically without any help from us. I find that deeply humbling. It shows that we live on a world with its own vast, slow dramas. But that does not mean the current warming is harmless or ordinary. The troubling part is not simply that the temperature is changing, but how swiftly. The planet has endured great swings before, but life had thousands or millions of years to adjust, migrate, and evolve. Our cities, our farms, our roads, and our ways of living are built on the assumption that the gentle Holocene climate of the last few thousand years will keep going. We have never had to ride out the faster extremes of the deeper past, with billions of people and intricate global systems depending on stability. Some changes we have already set in motion will last a very long time no matter what we do now. Warmer oceans expand slowly, and large ice sheets respond sluggishly. Even if emissions dropped sharply tomorrow, higher sea levels would likely persist for many centuries. Recent scientific reports suggest that we have already moved beyond the point where staying safely below 1.5 degrees Celsius of warming is realistic, and that avoiding much higher numbers will require rapid, far-reaching shifts in how our societies use energy, grow food, and move things and people. Those shifts will not be easy. They will touch nearly every part of life, from the cars we drive and the power that lights our homes, to the ways communities are designed and the choices governments make. It is hard to imagine us managing such a task if we cannot even agree on what is happening. Without some shared foundation of facts, it becomes simple to pick whatever story feels most comfortable and to walk in circles while the warming continues. That is why context matters so much. When we look back over ice cores, sediment samples, fossil shells, and all the other traces of deep time, a clear pattern emerges. The recent surge in global temperature does not fit the usual rhythms. It arrives too fast and too tightly bound to human activity, to the rise of industrialization, to the burning of fossil fuels, to the clearing of forests. You can debate what we should do in response. You can weigh different paths and priorities, but the basic shape of what is happening is written into the planet itself, preserved in ice and stone and the chemistry of ancient oceans. Those records do not bend to opinion. All around us, Earth's cycles continue. Orbits shift, axes wobble, oceans slosh, winds weave, and the core turns slowly in the dark. Sometimes their extremes bring hardship, long winters, droughts, storms, rising tides. Sometimes they bring calm. By learning how these cycles work, we give ourselves a better chance at living alongside them instead of being endlessly surprised. We, too, have become part of this tapestry now. Our actions echo into the climate, alongside the quiet pull of the moon and the tilt of the earth. Whether our influence will settle into some new, gentle rhythm, or flare and fade like a brief, disruptive spike, is a story still being written. It is possible to imagine a distant future in which our descendants have learned to shape climate deliberately, adjusting temperature and rainfall, the way we now adjust lights in a room. Perhaps one day, the great natural cycles will be only one element among many in a carefully managed system. But that day is far away. For now, our most important work is to understand the patterns we are already inside, and to see clearly how we are nudging them. Because whether or not we notice them, these cycles notice us. They set the stage on which we live out our days. The next time someone makes small talk and asks you about the weather, you will know that hidden behind that simple question is an entire story of tilts, tides, orbits, oceans, forests, fires, and time. Whether you share all of that or just smile and say, "It has been a strange season," is up to you. Either way, you will be hearing, beneath the passing clouds, the quiet ticking of a living world.